Okay, so let's look at a problem here in which we've got a satellite, and so put solar panels on it here, and it's got a rocket engine, and it's trying to change velocity. Now, there's several reasons you want to change velocity. You're in orbit, and you want to change to a different orbit. And so what you want to do is maybe speed up to an orbit that takes you out here. Now, you could just go straight out, to the orbit, but you'd have to change the velocity quite a lot to do that. Normally, we change the velocity a little bit, which pushes you into another orbit, which then you change the velocity again to get to the final orbit. So why the two-step process? Well, if you did it the direct route, you might have to have a delta V, or change in velocity, of 1250 meters per second. Okay, so let's say that your initial mass of your spacecraft is 735 kilograms. And so the question is, how much fuel do you need to do this? So what you would have to do is calculate the final mass and then figure out how much fuel it took. To do that, we use our second rocket equation. VF equals VI plus the exhaust velocity, natural log M initial over M final. Okay, well, V final minus V initial, that's going to be your delta V. So that's the delta V. So then we can say that delta V divided by V sub E, so divide through by that, is natural log M initial over M final. So we want to get rid of the natural log, so we have to do, so the exponential function e to the delta V over the exhaust velocity equals M sub I over M sub F. So that means that M sub F is going to be equal to M sub I e to the minus delta V over V sub E. Okay, so you need to know the exhaust velocity of here. And so let's say the exhaust velocity is going to be 495 meters per second from your spacecraft. So you plug in the numbers here, and the numbers, the M final is going to be 735 kilograms, e to the minus 1250 meters per second divided by 495 meters per second, and M final comes out to be 59 kilograms. Remember, M initial was 735 kilograms, so your delta M, that's your fuel. That's the fuel that you expended right here. That was 676 kilograms that you expended. And so that means almost all of your spacecraft was fuel. So obviously there's problems. So the problem is, you got your spacecraft, you got the exhaust here, and you're trying to change velocity here to go from one orbit to another orbit, and you're having this enormous amount of fuel it takes to do that. So what do? Well, this is the problem. This is why astrodynamics is very difficult, because you want to change your spacecraft. Your space has to be carrying all the fuel with it. It's not likely you're going to have a gas station in orbit to go refuel. And so the question is, what do? Well, you have to actually calculate what is the least energetic way of doing it. In other words, is there any way that you can get into a little bit different orbit that sort of spirals outwards and so forth? Could that do it? Or maybe what you need to do is change something, because remember, you're using too much mass. So your delta V, it takes a certain delta V to get from one to the other. And remember, the delta V was escape velocity, natural log, initial mass over final mass. So you can either pick a different delta V that would get you there, except sometimes that's not possible. So the only other possibility would be to have another rocket boosting this, pushing it along, which you then drop off, and that would let the delta V not be part of your satellite's rocket motor, but from third stage of a rocket. So that means you got to plan in advance where do you want your satellite to be. You can't just put it in orbit and then change it. Okay. The other option is to design your engine with a bigger delta V. Now, that's something that has been interesting because there have been spacecraft that have been experimenting something called ion drive. And with an ion drive, you basically use solar panels to use electrical energy to accelerate individual atoms and spew them out. Okay, so you spew out one atom at a time at near the speed of light. So that means the the exhaust velocity here is maybe, maybe 1/10 the speed of light. So 3 times 10 to the 7 meters per second. That is enormous, but your dm/dt is going to be very small because you're spewing out one atom at a time. And so what does this mean for you? Well, two things. Remember the minus dm/dt times the exhaust velocity. That's your thrust of your rocket right here. So that's your rocket thrust. Okay. If this is very small, even if that's very big, if this is very, very small, that means your thrust is very low. So ion propulsion has an extremely low thrust. That means the acceleration is very, very small. However, because the exhaust velocity is very high, your delta V, which is going to be exhaust velocity natural log of mi over mf. If this is very big, that means your delta V can be very big. So that means that even though the acceleration is tiny, your final velocity can be very high. So this is not very useful for manned missions because you want to get there relatively quickly. The European Space Agency sent a spacecraft to the moon using this rather than taking 2 or 3 days like a manned mission would do. Instead, it took weeks to get to the moon. Okay, but it took very little fuel to do that. Likewise, United States, NASA did an experimental spacecraft called Deep Space One that went past a comet. It took years to get there, but the final velocity was extremely high. And so it took very little fuel to get that very high velocity. It just took a very, very long time to get that high velocity. And so that's your trade-off right here. So that's the idea of ion propulsion, and it relates to these two rocket equations.